Well, I'd like to introduce Professor Shirley Dyke. She's presenting remotely from University of Purdue, or Purdue University. Shirley, she held a joint appointment and holds, I guess, a joint appointment in both mechanical engineering and civil engineering. And she's director of the Purdue Intelligent Infrastructure System Lab at the Bowen Lab. She holds a Bachelor of Science in Aeronautical and Aeronautical Engineering from the University of Illinois in 1991. And she has a PhD in Civil Engineering from the University of Notre Dame in 1996. Her research focuses on the development and implementation of intelligent structures, and her innovations span structural control technologies, real-time hybrid simulation, machine learning, and computer vision. She's currently leading an NS-funded research virtual community focused on advancing hybrid simulation called MEX. So with that, I'd like to turn it over to Shirley, and we appreciate your remote support, Shirley. Thank you.
Thank you very much. It's a pleasure to have a chance to tell you today some of the things that we've been working on and what the community is thinking about in terms of the future of hybrid simulation. Most of my work has been in real-time hybrid simulation, but as you saw, there's a great deal of other work that's also been done in the field of hybrid simulation. I'm going to mostly focus on the real-time aspects of hybrid simulation this morning. First, maybe a little bit of introduction to myself. The title, Bridging the Gap with Real-Time Hybrid Simulation. So I'm going to be talking about the past and the future of this methodology and what types of things have been done and where we're going from here. So my laboratory, as was mentioned, is at Purdue University, and the Intelligent Infrastructure Systems Lab is focused on minimizing risk and improving resilience through different types of technology, sensors, devices, control. And a couple of the things that we've been working on is autonomous visual inspection. How do we use large volumes of images and actually detect damage? But the right-hand image is what we call the Cyber Physical Instrument for Real-Time Hybrid Simulation, located here at Purdue. It's a facility that is designed specifically to develop new methodologies that could then be taken to other laboratories, used on larger specimens, larger systems, but we have the ability to rapidly do experiments here using real-time hybrid simulation and test out new ideas. Some other things that we do are related to structural health monitoring and looking at different ways to use sensors for gathering information about the condition of a structure, as well as structural control. Using specifically, most of what we've done is on magnetorheological fluid dampers and how those could be used to reduce the response of different types of structures, buildings, bridges, or even automotive or aircraft applications. But on the right-hand side here, you see this multi-hazard engineering collaboratory on hybrid simulation. And this is a new project that NSF funded, the idea being to bring together a group of researchers that can share ideas, that can build capacity for hybrid and real-time hybrid methods toward different types of applications. This is a field where we need a lot of different input from different types of experts. For instance, we need people in control theory, as well as people in structural testing, as well as people in signal processing, etc. And so what kind of material has to be developed? What kind of theory, what kind of methodologies have to be developed to really advance this technology and turn it into something that can be used every day in our laboratories? So many of you, I suspect, are very familiar with dynamic testing. In civil engineering, we use dynamic testing for understanding our systems, for validating our systems. We do this at large scale because, as Art was mentioning a little while ago, it's very important to study these systems in their realistic condition at large scale, at full scale, if possible. This is also true in automotive applications, aircraft applications. We do a variety of dynamic testing. It's always best to test it at the largest scale possible so that we get very realistic behavior. Often in civil engineering, this is done with a shake table. This is one of the best instruments for testing full-scale systems under the most realistic situations when it comes to seismic applications. However, there's a great many challenges as well, in the sense of to test things out at full scale, you need something like this. So this is in Miki City, Japan. This is the largest shake table in the world, and it is 15 meters by 20 meters, and it has a payload of 1,200 tons. This was built in 2005. It was recently upgraded so that it's now a 6 degree of freedom facility in 2016. But this type of facility is extremely expensive to run as well. So it's very important for those necessary tests, but if you can do things with less cost, more rapidly, studying different scenarios very quickly, then that also gives you new opportunities to test out a variety of things in the laboratory before you take them to a facility like this. And actually, even a facility like this has limitations, right? What happens when we have these long-scale bridges, extremely tall buildings? We can't put even these systems, we can't put them in a single laboratory, even a facility as large as this one in Japan. So what we've been doing for the last several years, this is a method, I think it's more or less the real-time aspect started around 2004 or 5, is to do hybrid simulation at real time. So this is important if you have a system that has significant coupling between the physical system and the computational system. And I'll talk a little bit about how we break these up into physical and computational systems in a few slides. But real time is important when you have some sort of rate dependence in your system, or when you suspect you have rate dependence and you need to understand it. But the advantage of this is that we can very rapidly change our computational system. The blue part of this diagram is meant to represent the computational system. The gray part is meant to represent the physical system. And I use a transfer system or a hydraulic actuator or many hydraulic actuators to impose realistic conditions upon that physical substructure based on what my computational model tells me to implement in real time. So I'm not determining what those conditions are going to be in advance because I don't understand this physical substructure, so I can't model it. The goal is to actually, in real time, take measurements off the physical substructure and impose those on the computational substructure, and then actually bring those back into the physical substructure so that I can understand how it will respond. And so the idea is to be as realistic as possible, but the advantage is that blue part of the structure, the computational substructure, in just a few minutes I can change to a new model. I can test a different scenario. I can test a different input. I can test it under totally different conditions using the same physical substructure if I'm not damaging that substructure, of course. This can be done with a hydraulic actuator, but it can also be done with shake tables and other types of systems, and I'll mention a little bit about that at the very end as well, some of the newest applications of this idea. So real-time hybrid simulation is a cyber-physical, time-efficient, cost-effective technique to integrate physical testing with computational simulation. So one of the earliest frame tests that was done was this project that we had at Lehigh. This was a NICE project funded by the National Science Foundation in the United States. And it was a team of researchers, 10 faculty from 5 different universities that were all involved in doing real-time hybrid simulation. There's 3 actuators located in this figure. But the frame that you see, this orange frame with the chevron braces, is the test specimen. That's the physical substructure that we used. You can also see at the bottom that there is an MR damper, a magnetoroidal fluid damper, And the goal of this project was to develop performance-based design strategies that were suitable for structures with semi-active control devices such as MR dampers. So we had options to put a couple of MR dampers into this frame, but the entire structure was actually a 6-bay by 6-bay 4-story structure. We modeled 2 of those frames in the laboratory. We built 2 of those frames in the laboratory. The rest of it was modeled, as well as the bulk of the mass was modeled in the computational model, which is over here on the right-hand side. And we learned a lot from these tests. As I said, I believe these are the first frame tests that were done, especially with multiple actuators, of real-time hybrid simulation. And this really launched a series of questions in our minds that said, how do we do this even better? You know, we had a lot of success in these tests. We had hydraulic actuators that were very large relative to our specimen, but we also had to deal with control issues that were associated with the actuator dynamics and the control structure interaction. And so this brought up a whole bunch of questions that led to some of the things that I'll talk about today. So what I would like to talk about today is some of these experiences, how we dealt with those experiences, how we learned from them, and how we developed some new methodologies and procedures by which we use to perform real-time hybrid simulations. Now, every time we do an experiment, that's the procedure that we basically follow. But then I'm also going to talk about this MEX collaboratory on hybrid simulation, the mission, things that we've been doing recently, things that may be opportunities of interest for people in the audience, but mostly how is this community breaking down barriers and building capacity across the country, across the world, in terms of using hybrid simulation and real-time hybrid simulation methods. And then I'll briefly mention some of the future things that we're looking at that we hope that we at the IISL are hoping is going to propagate through the community and improve these methods even further. So we know what hybrid simulation is. We have a numerical or a computational substructure. We have a physical substructure. We're sending data from our computational substructure into our physical substructure. We're measuring some responses, and we're sending those back. But this actually requires a lot of different expertise, right? We have experimental methods, control, hydraulics, signal processing, data acquisition is all a part of doing that, the physical aspects of it. On the computational side, we have to have computational modeling methods. We have to know how our algorithms are working for integration. We have to do structural dynamics well. We have to have embedded systems that are able to do the execution in real time for these methods. And then we also have to consider what uncertainties may be present, what noises may be present in our system, and what is actually happening in that test. When we do hybrid simulation, there's an extended time. We don't have to worry so much about actuator dynamics and the timing associated with that. But when we do real-time hybrid simulation, all of these issues become important considerations. So we want to do real-time execution of our numerical models, of our controllers, so that we can minimize the impact on the results of doing this test in any sort of different way than what happens in the field. Right? Even any type of testing in the laboratory is always going to be a little different than in the field, but we always have to minimize that. That's our objective. So we've been looking at these issues. And if you think about it, this is such a multidisciplinary field. Hybrid simulation is viewed right now anyway as a test method that's primarily used in earthquake engineering, but it pulls in people from all different backgrounds. It pulls in people from the data acquisition, the signal processing background, the control theory, and thus it seems very complicated on the surface, but it's not really as complicated as it seems, I believe. But the questions that we've been we've been thinking about are related to what does it mean to have a successful RTHS. I said that we're always aiming for our tests to be as realistic as possible. And one can impose a displacement on their system, and the goal is to achieve some sort of coupling between those systems. But what happens when we do break up the system, and how can we make it as realistic as possible? These are the questions that we've been thinking about quite a bit for the last 8 or 9 years, 10 years. And what are these two systems equivalent? Well, equivalence is kind of a concept that depends on the purpose of the test, right? If the purpose is to get strains and stresses out of our structural materials, or if the purpose is to replicate dynamic behavior, or if the purpose is to study a new control device, we may have different meanings for equivalence. And so we need to kind of keep that in mind when we begin such a test, is what are we trying to achieve? The other consideration that we realized a while back, and many other groups did too, I have to say, is that actuator dynamics is a necessary consideration. When you send a command to a hydraulic actuator, so say we have our hydraulic actuator, our transfer system, when you send a command to a hydraulic actuator, it actually doesn't respond instantaneously. It has dynamics, just like the building has dynamics. And so our objective is to understand this behavior so that we can minimize that, the effect of those dynamics in the closed loop. So we have a desired signal in blue, that's the command. That's what we're trying to send to our hydraulic actuator. But in reality, the hydraulic actuator has a few milliseconds. A reasonable amount is typically 50 to 100 milliseconds of dynamics, of delay. And there's dynamics associated with the amplitude, there's dynamics associated with the phase lag, and our goal is to minimize that delay by inserting some type of control system. So the control system is one of the aspects that we've been focused on, is how do you develop better controllers. You can do this with PID. It's not our method, but it certainly works under many circumstances, but there are extreme cases where you want to do even more. So if I just close this loop, the loop on the left-hand side, and I take that measured force and I send it to my numerical structure and I compute that and just send the displacement right out of the computer to my hydraulic actuator, then I can potentially have challenges or errors in that test method. So by minimizing this loop, I can get rid of those dynamics, and I have a much more accurate test. So on the right-hand side, previously here, this is potentially what could happen in a sensitive system if I don't include some type of control in my loop. But if I insert a controller, a hydraulic tracking controller, to account for those dynamics and to improve those, minimize the delays, I can actually get significantly better response, and it looks very much like the reference system that I was intending to replicate. So when we were at Lehigh, and in the course of this project, we did some large MR damper testing. So these are pictures of what looks like a hydraulic actuators attached to magnetoroeological fluid dampers. However, in reality, both of these are hybrid tests. So both of these hydraulic actuators are driving MR dampers using a command signal from some sort of command input from a building, from a numerical model of a building. And in both cases, we saw unexpected behaviors. This is way back in 2010. We saw unexpected behaviors because when we changed the characteristics of the magnetoroeological damper, for everyone's benefit, a magnetoroeological damper is a damper that is controllable. So it has magnetic fluid inside of it. If I change the magnetic field, I can rapidly take this device from something that produces a couple hundred kilonewtons to something that produces a couple thousand kilonewtons. And when I do that, when I change the behavior of my physical test specimen significantly, then my controller has to be changed as well. This is something that we observed, and we didn't understand it as well at that time as we do right now, but it motivated a lot of the questions that we've been looking into. So what we've really been doing as a whole is looking at a procedure so that the outcomes of our test are as meaningful as possible, so that if a researcher wants to study a particular aspect of a test, then they can design their test so that the errors are minimized in that portion of the test, so that we have the most success, really, is what we're saying. We have the best set of results toward that particular objective, toward meeting that particular objective. And so the things we've been thinking about are twofold. If you represent this test, this is the physical specimen, right? We have hydraulic controllers, we have a hydraulic actuator, and we have a physical substructure. If we represent that with a block diagram, the areas where we really need to understand this are the controller that closes this loop, that actually closes the loop and controls the hydraulic actuator, but also the decisions that go into how do we take this physical substructure and this computational substructure and break it up so that our testing is as good as possible, as accurate as possible. So one of the issues is, how do you partition your system? I mean, how do you actually break up your system in such a way that you can test it with as much accuracy as possible? So the left is just a potato diagram showing a structure. We have a whole structure. It has these components, but I need to figure out how I'm going to break it up. How am I going to break it up so that I can do a test? Now, originally, we used to say, well, let's just take out this part and put it in the physical specimen, take out that part and put it in the numerical specimen. It's very logical to do it that way, but we'd find that sometimes the test was very difficult to perform then, and there are ways to choose how to break up the structure so that we can have an easier test to run with more accuracy. So these are the types of questions. We always want to get as much realism, even if the errors are tiny. We still want to get as much realism as possible in our tests, right, to understand our system. So the question is, how do we do what's shown on the right? How do we break up our numerical our complete structure into a numerical substructure and then a physical substructure, so that when we attach our hydraulic actuators and we do this physical test, that we get the best results we can. So what we developed was a procedure for doing this, and we did this based on indicators, some predictive indicators that were intended to predict stability and performance of the test. So we developed a series of predictive indicators, and this methodology is the result. So if a researcher chooses a particular partitioning configuration, and then they also know the hydraulic actuators they have in their laboratory, they know basically what the characteristics of those are, then they can start with that. They can compute these predictive indicators. They can understand what their minimum requirements are for the time delay in the actuators, for example, for the performance that their objective is in trying to replicate some complete system with their hybrid system, their partition system. Then they can look at designing a controller and seeing if these minimum requirements and the tracking performance are possible. And if that's acceptable, you move forward and you go ahead and you do the test. But if not, before you actually build anything, you have the ability to separate your system into a slightly different system that may be easier to test. That's the objective, to get really good results from the test. So we might want to make small changes to our test setup to allow for the testing to proceed with greater accuracy or for easier ways to do the test. So once you have those predictive indicators, you can design your control system and move forward with the test. And so we've done this over the years with a number of different experiments. This is one experiment that we did around 2012 with researchers from the Technical University of Denmark, and their goal was to look at wind turbines. And they have wind turbines that are out in the ocean, and they have wind and wave interaction that are both affecting the dynamics. They're both exciting, these wind turbines, and thus they're not as efficient as they could be. And so they wanted to put some damping devices into these wind turbine towers, and the objective was to use hybrid simulation, real-time hybrid simulation, to figure out how to best do that. So the inputs were wave loading, and those were basically done as a separate input, just like an earthquake would be input into our computational model. We used wave loading instead as the input to our computational model. And you could envision extending that to many other types of applications, like wind, like roadway irregularities in an automotive application. The device itself is rate dependent, so we had to use real-time hybrid simulation because the device itself was rate dependent. But this was a particularly challenging problem because these towers tend to have a very broadband distribution. The first mode tends to be very low, around 0.25 hertz. But the second mode is very high. It's very far removed from that first mode, and it was around 80 hertz. And so designing our physical test apparatus and doing the control design for that test was something that took us a bit of effort. We learned quite a bit in that process. Another experiment that we did, this was with Harbin Institute of Technology in China. And this is it's about a 14 foot, I think, frame that is representative of a 3-story building. And our goal was to put magnetorheological fluid dampers in the first floor of that structure to reduce its response during earthquakes. And here, our real goal was to compare the real-time hybrid simulation method to a shake table test. And this was one of the earlier tests we did for research purposes to do that, trying to actually do that comparison, just to understand how well it was reproducing the shake table test. And it came out extremely favorably. We did shake table testing with the MR dampers in Harbin, and then we also used a universal testing machine there, a very large universal testing machine, to do some hybrid simulation using this type of arrangement shown in the center bottom of this diagram, where we have a numerical model of the building and we have an experimental substructure, a physical substructure that is the MR damper being tested. But we did this test with 2 different configurations. One was a universal testing machine with a very large actuator, happened to have a lot of noise. The other one was basically the small setup that you see here, where we have a 2,000-pound hydraulic actuator working with a 1,000-pound MR damper in its on configuration. And both tests actually produced very similar results, different controllers, but both tests were able to produce extremely good results in terms of representing the global behavior of this structure with such a control device. So that was very positive. The only challenges that we had there were that if you have an actuator that needs a large volume of oil, obviously a larger actuator needs more oil, and so if you can't supply it quick enough, then you may miss some of the peaks in the response. And that was one of the challenges that we had, but that's easily overcome by just having a larger pump. So that was an excellent learning activity as well. But the idea is that we were able to very closely reproduce the shake table test using this real-time hybrid simulation setup. Another experiment that we did is very different than these other ones that I mentioned. We used the same numerical model of this three-story frame structure, but we did it for a totally different purpose. And the purpose in this experiment was to validate wireless control and wireless sensors. And so we were, because if you're doing a control experiment for wireless, if you're doing a wireless control experiment using MR dampers, you don't want to impose sensor failures on the real system, right? You're going to have large amplitude response, but you can very safely do this in a real-time hybrid simulation mode. So what we did was we actually used the computational model of this building. We represented the wireless sensors in the computer as well, and then we used the hydraulic actuator and the MR damper as the control device, but we were able to study what happens if different failure scenarios. So we tried a variety of different failure scenarios where data loss might be anywhere from 10% to 100%, which means a total failure of that sensor. And then we looked at how did the control system perform under those conditions. So this brings up many possibilities for the future to study. You know, Internet of Things is something we've been talking about. Is there a way to use real-time hybrid simulation to explore the success of the Internet of Things, different types of sensors that are used for different purposes within buildings? And I suspect there's a lot of ways in which that could be done in the future. Another aspect that we've been looking at is how can you actually, if you don't have a system if you have a system in your physical setup that you don't understand, can you learn from it? Can you identify your models and feed those back into your numerical substructure so that you can improve that modeling capability and you can improve your overall test? So if your structure is actually changing, if your physical specimen is being damaged, can you update the parameters of your model and then continue running the real-time hybrid simulation in that mode? Now, we did not do this in real time. It was done at about 1/4 speed because of the updating algorithm required a tremendous amount of computational power. But what you can see here is that we were able to grab onto the behavior of the physical specimen after a few seconds of simulation and then improve the overall test as it propagated, as it moved on. And so this is another tool that we could pull into RTHS and have at our disposal for improving our test results. So let me talk a little bit about this community. And if you're interested in resources associated with real-time hybrid simulation, we have over the years put together a few demonstration codes. And these demonstration codes are posted for anyone to grab and try out. One of them, the one on the right, the first one, was focused on simply demonstrating real-time hybrid simulation and the effects of actuator dynamics. It's a short MATLAB code that anyone can download and try out on their computer. It does not run in real time. It's a very simple code. The second one is a demonstration of the same thing for base isolation. And the third one is actually a virtual real-time sample code that is meant to be run on 2 different computers in a distributed sort of environment. So you can actually have, you can actually use this, download it. It requires MATLAB's XPC system, but you can actually download these if you want to learn something about real-time hybrid simulation and you don't have a lot of experience with actuator dynamics and such. These are tools at your disposal, and they are posted in DesignSafe. I'll show you the link in a few more slides. But this leads me into this research coordination network. So the National Science Foundation, a year and a half ago, has funded what's called a research coordination network, which is a virtual community. So the idea is that maybe once a year we get together and we talk about the needs within this community, but most of the time we're all interacting virtually through this website, And we did have our first workshop back in December. That was held in San Diego, and it was titled Breaking Barriers and Building Capacity. And the goal was to get together and start working on a research agenda. What theories and what methodologies, what techniques need to be developed to advance the testing methods associated with different types of hybrid simulations so that we can extend these into more testing domains, go into other disciplines. Basically, we can just make it more powerful and more useful to people in the community. So what questions can we all work on together? And there's three main goals. One is establishing partnerships within the United States and around the world, both trying to work together with researchers of common interests. The second one is building capacity. Building capacity means bringing this technology and this possibility to people who have not used it in the past. And the third is this research agenda, which is posted on the website as well. And so this is a website. I'll give you the link again at the end of the presentation, but this is what our website looks like, the purpose, the information that's available. You can get to it through designsafe.org. And we have a series of workshops. We're going to have one every year, basically, to talk about these methods. But we also have resources. And the resources are being updated all the time. There are the tools that I showed you earlier, that's samples, and there are a series of reports going back to the history of early hybrid simulation methods that are posted here, but going as far forward as the recent journal papers and the primer and dictionary that was developed for researchers that are new to hybrid simulation so they could get comfortable with the terminologies and the ideas and the methodologies without necessarily worrying about how do I do it in the laboratory yet. Another item that's posted is a benchmark problem. So benchmark problems are useful. They've been developed for the last 20 or 25 years in the structural control community and the structural health monitoring community. But the idea is to have a common problem where different researchers bring different methodologies and try a problem, a single problem, figure out how they would tackle that. And we've built a benchmark problem in real-time hybrid simulation that was just posted a month or two ago. The focus of this is on designing the transfer system tracking controller. So this has the physics-based models of the control structure interaction, the physical substructure, finite element models are there. Everything that you would want for a straightforward single actuator real-time hybrid simulation test is provided. The models, the simulink code, and then we also provided a sample design that is not meant to be a very strong design. It's just meant to give you an idea as to what researchers may want to do with this, and then methods to evaluate that. So this is available as a code package and a paper for anyone to download and use. And once that is done, we also have a special issue of a journal that is going to be coming up. The deadline is the end of the year for the paper to be due. So if someone's interested in doing research on this topic and they want to understand real-time hybrid simulation, they want to try this problem with their own methodologies and then write a paper about it, there's going to be a special issue. These websites I also have at the end of my presentation. So in summary, hybrid simulations are expanding the types of tests, and they're very useful for understanding global response and many other purposes that you might have in mind, validation, for example. But to utilize these methods, it's very helpful to think about the configuration of the test and how you're going to actually perform the test, what control you might need in order to be the most successful that you can, have the best outcomes of your test. And it has strong potential for many other applications. In addition to dynamic testing, in addition to earthquake engineering, complex systems, anything with significant interactions does offer this as a possibility. Most of the things, or many of the things, have been related to smart structures and control devices that are done by changing the setup, changing the computational model rapidly. A couple of future directions I'm going to mention. One is the fact that when we're trying to do RTHS, often we don't know what the physical specimen is. That's the purpose of the test. So we've been focusing on self-tuning controllers that are suitable for these types of systems with uncertain dynamics. We don't understand the dynamics completely. We might have a rough idea as to how much force it's going to provide and when it might break, but we don't really understand how to model that system. So we've been testing this on this little device at the bottom, which is just mass and a stiffness element that breaks. And we've found that when we put a controller on it, on the right-hand side, you see a controller. The response, even though my device has broken, which occurs right before 3 seconds, and I have a force dropped from a high force level down to 0, my controller continues doing what it's supposed to do. So that's a good sign that this controller is suitable for real-time hybrid. We've tried it in some other tests. I just haven't been able to update those figures. But we do have some implementations of this for closing the loop with real-time hybrid simulation as well. And the other thing that we're focusing on is how to do more computation in that tiny amount of time. So right now, one of the limitations is that if you have a single processor able to do real-time processing, that the computation is limited in your finite element model. So if we have the ability to parallelize that and then actually do that in real time, the computation should be done in real time, then you have the power to run much more complicated finite element models with these tests. And we've been looking at ways to schedule the tasks on parallel computing so that we can actually achieve that. We have done this with parallel computing, but actually controlling and scheduling the tasks is something we're thinking about for the future. And just briefly, let me mention the natural hazards engineering research infrastructure is something that is relatively new, funded the last 3 years, 2 to 3 years, by the National Science Foundation. It includes many labs, but what I want to mention specifically is that hybrid simulation is moving into the wind community. And so this is the Wall of Wind at Florida International University, and they are thinking, they have some projects that are just starting up on how to use hybrid simulation and real-time hybrid simulation. The issue here is that the computational burden becomes even more challenging because they're trying to simulate things at 20 times the speed of an earthquake test, for example, 20 times the speed of the real world. And at the University of Florida, they have a nice wind tunnel shown here on the left, which has a lot of versatile capabilities to change the terrains in a quick way. And so they're looking at a version of real-time hybrid simulation where they're actually morphing the structure so that they can understand how to best create the right wind profile that they're interested in. So I'm not going to say a whole lot more about those, but these are futuristic applications. They're starting to come online right now in terms of wind engineering, and so there is a wide variety of interests and different communities that are working on hybrid simulation and real-time hybrid simulation. And I'll just show my contact information if anyone's interested, and the benchmark problem and plenty of other information is available on this MEX page on the right. And if you're interested in joining the announce list, you can feel free to just send an email to mex@purdue.edu and then just say, I want to join. And we'll add you to the list, and then you can get announcements from that community.